Imagine stepping outside on a cool September night in 1859. You look up, not at a familiar starry sky, but at a breathtaking celestial ballet. Ribbons of green, pink, and crimson light dance across the heavens, so bright you can read a newspaper by their glow. This was the Carrington event, a moment when the sun reached out and touched our world in a spectacular and slightly terrifying way. People from Cuba to the Rocky Mountains witnessed these auroras, lights normally reserved for the polar regions. It was a beautiful sight, a truly cosmic spectacle that filled people with wonder and awe, a direct connection between our small planet and its magnificent star. But this beautiful light show had a hidden power. Down on the ground, the world's brand new technology, the telegraph system, was going haywire. Sparks flew from the machines, shocking operators, and even setting telegraph paper on fire. The invisible energy surging through the earth was so strong that some operators disconnected their batteries and found they could still send messages, powered purely by the storm from the sun. It was a fascinating, almost magical occurrence, but it was also a warning, a glimpse into the immense power our star holds over our fragile, fledgling technologies. It showed us that the same sun that gives us life can also disrupt it. Now let's fast forward to today, 2025, August 12th. Our world is no longer connected by simple telegraph wires, it's a global web of intricate power grids, satellites, and the internet. We rely on electricity for everything, for our lights, our hospitals, our communication, our food supply. A storm like the Carrington event today wouldn't just be a curiosity, it would be a catastrophe. Simulations of a modern-day Carrington event paint a chilling picture. They show not just flickering lights but a widespread cascading collapse of the power grid. A technological shutdown that could plunge entire continents into darkness for weeks, months, or even years, fundamentally altering our way of life. Our sun, that familiar life-giving star, is a colossal ball of burning gas. It seems calm and steady from 93 million miles away, but it's actually a dynamic and sometimes violent place. On its surface, magnetic fields thousands of times stronger than Earth's twist and writhe like giant celestial snakes. Sometimes these magnetic loops become so tangled that they snap, releasing an enormous burst of energy. This sudden intense flash of light and radiation is called a solar flare. It's the sun's equivalent of a lightning flash, but on a scale that is almost impossible for us to comprehend, releasing the energy of millions of hydrogen bombs in just a few minutes. A solar flare is just the beginning of the story. Often these powerful explosions also hurl a massive cloud of solar plasma and magnetic fields out into space. This is a coronal mass ejection, or CME. Think of it as the sun throwing a colossal magnetized cannonball across the solar system. This isn't just light. It's a billion tons of superheated gas traveling at incredible speeds. Most CMEs miss the Earth entirely, flying off harmlessly into the vastness of space. But sometimes one is aimed directly at us. It's a game of cosmic chance, and our planet is a very small target in a very big shooting gallery. When a CME is blasted towards Earth, it begins a race against time. These clouds of charged particles can travel at astonishing speeds, some reaching over 5 million miles per hour. At that velocity, a CME can cross the vast distance from the sun to the Earth in less than a day. The fastest ones, like the one that caused the Carrington event, might make the journey in as little as 17 hours. This gives us an incredibly short window of time to prepare for its arrival. So what happens when this magnetic cloud of solar particles finally reaches Earth? Our planet has a natural defense, its magnetic field or magnetosphere. This invisible shield deflects most of the solar wind. But a powerful CME is like a tsunami overwhelming a seawall. It can distort and compress our magnetosphere, causing immense geomagnetic turmoil. This rapid change in the Earth's magnetic field creates something very dangerous on the ground. It induces powerful, uncontrolled electrical currents that surge through the long wires of our power grid, a phenomenon known as a geomagnetically induced current, or GIC. These rogue currents are the real enemy of our electrical infrastructure. They flow into the heart of our power grid, the large power transformers. These are the giant humming metal boxes you see in electrical substations. Their job is to change the voltage of electricity, stepping it up to be sent over long distances and stepping it down again so it can be used safely in our homes. They are designed to handle the smooth, alternating current that powers our world. But the GICs from a solar storm are like a form of direct current, a type of electricity that transformers are not built to handle at all. This unwanted direct current is like pouring sludge into a finely tuned engine. It causes the transformer's magnetic core to become saturated, leading it to overheat dramatically. The internal temperature can skyrocket in a matter of minutes, causing the transformer's copper windings to melt and its insulating materials to break down. The result is a catastrophic failure. The transformer can be permanently damaged, effectively destroyed, cutting off the flow of power from that substation. It is a silent, invisible assault that happens deep within the transformer's core, turning a vital piece of our modern world into a useless hunk of metal. The true danger lies in the domino effect. Losing one transformer is a problem, but a severe solar storm could damage hundreds of them across a continent simultaneously. These are not items you can buy off a shelf at the local hardware store. Large power transformers are custom-built, weigh hundreds of tons, and can take more than a year to manufacture and install. If a significant number of them are destroyed at once, we simply don't have enough spares to replace them quickly. This is the scenario that could lead to a long-term, widespread blackout, a return to a world without the electricity that underpins our entire civilization. Facing such a colossal threat, it would be easy to feel helpless. But humanity is not just sitting by and waiting for the sky to fall. We are watching back. Our first and most important line of defense is an early warning system, and at the forefront of this effort is NASA and its partners. We have a fleet of spacecraft strategically placed in space, acting as our celestial sentinels. Their one job is to stare at the sun, 24 hours a day, 7 days a week, looking for the telltale signs of a solar flare and an Earth-directed CME. They are our cosmic lifeguards on the lookout for dangerous waves. The star of this fleet is the Deep Space Climate Observatory, or DSCOVAR satellite. It is positioned at a special place in space about 1 million miles from Earth, called the Lagrange Point 1. From this vantage point, it sits directly between the Sun and our planet. This means it can see any solar storm coming our way and measure its speed, density, and magnetic field properties directly. When a CME rushes past DSCOVAR, the satellite can give us a crucial final warning, a heads-up of anywhere from 15 to 60 minutes before the storm impacts Earth's magnetic field. It is our final tripwire. This warning, though brief, is absolutely vital. It is transmitted to forecasting centers on the ground, like the Space Weather Prediction Center in the United States. Here, scientists work around the clock interpreting the data from DSCOVAR and other solar observatories. They run sophisticated computer models to predict which areas of the planet will be most affected and how severe the impact will be. While power companies work to protect the massive grid, what about the smaller electronics that are essential to our personal lives? Our phones, laptops, and radios could also be vulnerable to the powerful electromagnetic pulse that a severe solar storm can generate. This pulse can induce damaging currents in small circuits just as it does in long power lines. Fortunately, there is a simple and remarkably effective scientific principle that can protect them, discovered by the brilliant scientist Michael Faraday back in the 1830s. The solution is a device that bears his name, the Faraday cage. A Faraday cage is essentially a container made of a conducting material, like metal mesh or solid metal sheets. When an external electrical field, like an EMP from a solar storm, hits the cage, the charge spreads out across the conductive surface instead of passing through to the inside. Leave a comment below for a complete grid-down protection guide.